CI, continuous integration and continuous delivery practices are discussed in the first day. Then yesterday we discussed the config management, day 2, and today is the last day of the webinar. And we are covering the containers and the orchestration. So the same things, right? If you haven't enrolled yourself to the training door yet, please go ahead and enroll to the webinar. And that is where you can see the recorded videos and the presentations that I am uploading. So just if you haven't done that, please do it. These are the steps that you can go through. And yeah, about me, my name is Basil. I'm the CTO of Ravel Grid, to which I am a co-founder also. And we provide services such as migrating the monolithic application to the cloud native. So in case, if you have any requirement, if you or your company have any requirement to migrate your monolithic applications into cloud, and need any advice on the best practices to convert them into microservices or into cloud native applications, right? Just you can reach to me. This is my LinkedIn profile, and you have my contact email ID and LinkedIn profile, my phone number. So just feel free to connect on LinkedIn, get connected. So that's pretty much about me, and we will start. So I don't know. To learn today's webinar, you should have some previous knowledge on Linux, right? Running some sample software or sample programs on Linux. It's kind of required to understand the concept that we are discussing today. If you don't have those prerequisites, it would be a little tough, but try to understand those high-level concepts that we are discussing in this class. At least a basic operating system knowledge is mandatory. Okay, so we will talk about a traditional application, right? Let's not worry about the containers for now. We will talk about a traditional software application, or maybe a sample PHP program, or a sample Python application that your company manage. So what do you need as the runtime of this application? Let's say it's a Python program that you are developing, and generally every program that your development team write, it depends on a number of modules, right? The dependencies, I think we discussed these things when we learned the CI/CD training, CI/CD webinar. At that point of time, so any source code, any code that the development team write, it depends on a number of libraries, and apart from that, it depends on when you want to execute this program, or in other words, when you want to run this program on a machine. Assume at the end you have one production machines or a development machines. This is where this application will run later. So when this application run on this environment, maybe this machine should be ready for that, right? You want to run a Python program, you must have Python installed in it, or otherwise, if it is a PHP program that to be installed in it, it should contain PHP. Or to run this program, there are a number of modules that need to be present. So those modules need to be installed as well on this machine. So think about if you have to manage such machines and different configurations inside such machines, there are a lot of things that you need to take care, right? You should make sure that Python is installed, that the necessary modules are installed, then you have a runtime environment where you can copy this program inside this. Then probably it might need a web server if you want to serve this application to the people on the web. If it is a web application, then you need a web server for that. So there would be a lot of dependencies that you need in order to run your runtime. Maybe a software application that your company developed need to run on a Linux machines. So these many things are required. And generally this is how it used to be. And yesterday and day before yesterday webinar, this is what we have been discussing. At a later point of time, whatever applications that your company is managing will run in a machine. This is your runtime. and it would serve your application to your customers. So what is containers? Containers are basically a lightweight boxes, maybe I call it lightweight boxes, which contains everything that the program need to run, right? It would contain the program that you want to run. It would contain the library that need to be installed along with the program. It also is installed with the necessary runtime environment. For example, Python should be installed if you want to run a Python program. So Python is present inside this container. If you want a web server, that web server is also present inside this container. So, and it's very quite lightweight. And this is not a machine. It is just a logical concept that will run inside a machine. Right? And you can have n number of containers running in the same machines, hosting different software applications along with the runtime environment the application needs. So maybe I don't know if I am confusing the things. Let's just a sample example of a runtime. You have a Python program. You want to run the Python program, but what is the basic requirement? You need one machine where Python is installed. Then yes, you can run the Python program in there. Or you have a sample PHP program which you want to run. You need one machine, and inside this machine PHP should be installed. Then this PHP program you can execute inside these machines. You have a Java program. You should have the compiled Java program saved inside a machine. The machine should have the Java virtual machine software installed in it. Then this program can run in here. So right, this is what I call the environment or the runtime, and this is what the application is. So just think about this. Don't think about the machines. You have a logical concept where you can put together the environment along with the programs that you want to run or the applications that you want to run. So in other words, this container would contain everything that it takes to run that particular program. And this is a very lightweight containers, and it can run inside an operating system, right? It can run inside an operating system, and you can run many such applications in a single operating system. Think about that. And they look like a real machine. I mean, they are not. Make a note. There are no operating system installed inside the container. There is no external libraries set up inside this container. The container contains what it need for it to run. That's all. The operating system is installed in the machine which contains this, which is running all these containers. So think about this. You have a Linux, you have a Linux operating system. Sorry. Right? Think about this. You have a Linux operating system, and in this operating system, you have installed Docker, Linux or Windows, right? Doesn't matter. You can install Docker on top of your operating system. Then you decided that you want to create a Linux container. What you do is you will download a Linux container. I mean, you can download it from a registry. We will talk about that. Assume you created one container which is which appears to be running an operating system. It is not. The operating system is nothing but in your machine. Maybe this is your laptop, or maybe this is some Linux machine that you created somewhere. In this there is an operating system, Linux or Windows, and inside that you have installed Docker, which is nothing but a containerization tool. Then inside Docker, you created a number of lightweight containers. And these lightweight containers can be created from some official image that the vendor provides. For example, you want a Windows operating system to be running inside a container. You just download an official Windows image, then create a container from that, and it will appear to look like an operating system, but there is no operating system. The operating system is on your laptop, and whatever makes for this container to make it look like an operating system, those necessary libraries and binaries, everything are shared from the operating system. So there is no operating system in the container. The operating system is shared, it is on the host machine, and so is every container. So let's say you downloaded a image, created a container, and you can log into this container just like you would log into a normal operating system, just like you log into your laptop. You can install the necessary software inside this container, run a PHP program in this container, run a Python program in this container after installing Python, right? And in here you can install Java, then you can run a Java program. In here you can install PHP, then you can run a PHP program. So you have different applications that you want to run inside these containers. You would install them whatever you want in these containers. You will run whatever application that you want to run, and this containers does contain a very few number of libraries to make it look like an operating system, but the actual operating system is on the host machine. It will share it. It contains only your application and the environment where your application can run. So maybe making things more clear. When I talk about the source code, the code which your development team is writing, and in the previous classes I have told you at the end, they will run on a production machines and serve the software component to your customer. That's what happens. So the shopping cart, somebody is developing the source code of shopping cart, and there is one machine, assume a dedicated machine, something like your laptop, which want to run the shopping cart component. This is what we have been discussing, right? So a machine you serve dedicated for running this application. So you should install Java inside this machine. Then you will run the Java code or whatever code the developers have wrote for this particular application. So instead of this, think about this, you keep a Docker host machine, a machine where Docker is installed. So the development team, if they have to manually do the things on a machine, assume this is a normal machine without Docker. In such case, first they create the source code, they will write the source code, and later they want to combine the source code with the other libraries. They want to compile and build the source code, maybe create some artifacts, and these artifacts they want to run it on some test machines first. The test machine should look exactly like the production machines, because first you want to do a complete testing here before it will go to production. Maybe you do such multiple testing in development staging, different environment before you go to production. So instead of this, let's think about this. You created a developer working in his laptop. He installed Docker in his laptop. What that means is he can create one container in his laptop. This container, assume it will appear to run a Linux operating system, but remember the operating system is always on the host machine. The container is very lightweight. If you see the size of this container, it's going to be hardly 100 MB, right? That's all. It's hardly 100 MB that the container would be. And if you install an operating system, what is the actual size of a machine? In case of a container, it's hardly 100 MB. So what the developer does is he created a container, he's working on this container, he's developing the code. Maybe he's developing the code in his laptop. A folder in his laptop contains the source code. He is developing the source code. After he developed the source code, he will combine the source code with whatever libraries and binaries that are required, then create a executable file. This is the final file that can be tested, right? A final file which contain the code developed by the developer. It need to be tested. So first the developer will run this executable file in a container within his laptop. Then he will do some testing. And this is a very lightweight container. Now it contains the application along with the runtime environment, along with whatever extra modules that need to be combined. So everything this container contains. So the container has everything that the application takes to run, the most important thing. Then let's say a developer take a backup of this complete container. He create a new image. It's called image. The backup of a container, it's called an image. Then this image is copied into a Docker host in the testing environment. I told you different company will have different environment where they want to run some testing of the code before they go to production. So first they will run this image by creating a container on a test environment. They will do a detailed testing. A report would be generated. Now the same thing, it's tested looking good. Then now you want to go to a development environment. You want to test the same application in development environment. All you do is the same image you will deploy as a container in the development environment. Then you do the testing here. It is tested and verified here. If there is a problem, again the developer want to start from the scratch. He need to fix the problem. He make the code change. He will combine it with the libraries. Then he create the artifact, then run it inside the container. Then he will create a new image. Then this new image would be tested in the testing environment, in the development environment, in staging. Finally it will again run as a container in production also. And do you know how much time it would take for creating the image? Just couple of seconds, because it's a very lightweight container. It contains only your application. So just couple of seconds it would take to create an image. To create a container from this image, do you know how much time it would take? Less than 1 second to create a container from this image. That's what all it takes. So not only it will improve the time, right, that you need for the deployment. Otherwise think about this. If the traditional developer had to work in the traditional way that we discussed on day one, first developer would develop the source code. Then first he will do a building in his laptop, and building takes time, right? You want to download the libraries, compile the source code, then create the artifact, then run the artifact on developer's laptop, do a lot of testing. After verifying, the developer would give this source code to, let's say, SCM tool. Then from the SCM tool the code would be taken. Then the code is, before the code is deployed into the testing environment, again the code is built, the libraries are downloaded, then artifacts are created, then it is deployed here. And when you deploy it here, maybe this machine look very different than the developer's laptop. Initial test were run on developer's laptop, but maybe this machine is running a different operating system than the developer is running. Or maybe this machine has Python 3 installed, but in developer's laptop it is Python 2 that is installed. So these kind of differences can be there in the environment where you are testing it. So you are actually out of sync. The same code, when you test it, you must make sure that the code is tested in the same environments, right? A code that will run on Python 2 environment, it can run only on Python 2. It won't work on Python 3. So developer did some testing. Maybe if the environment is wrong, then you would actually get some false positives, which is not good, right? Right? How much time individual people need to think, or it will take time to identify that okay, this was the problem, right? That itself would take time. So when you use Docker, it's the same image is deployed in every environment. Same image developer used to create a container in his laptop, same image is later used to create a container in the testing environment. Same image is used in development, staging, and finally the production to create these containers. So these containers are identical, and this containers contains the environment also. That means, let's say it's a Python program that need to be tested. This container or the image already contain Python 2. Then you run a Python 2 container where you run the test. Here also you run. So this environment is embedded within the image itself. You are not dependent on the host operating system in each environment. The best thing about Docker. You get you get a unique status across all your environment is what Docker can do, right? I don't know, right? Just it's little difficult to grasp if you are new to these things, right? But yeah, just at least those who are new to system administration or development, I hope you are able to relate things, right? Just think about executing a sample program on a Linux machine. You need a Linux machine for that, first of all, and the machine should have an operating system that support, and there should not be any conflict between the operating system and the environment, right? Let's say you install Python 3 in Windows, you install Python 3 in Linux. There's a good chance that same program can fail on Windows and it work on Linux. These kind of issues are there. Actually, the environmental issues are there, and today's teams are facing these issues. Developers are probably using a Windows PC and they have Python 3 installed in their Windows PC, and on the development environment it's a Linux machine running Python 3. Maybe the same program which run on Windows might fail on Linux. There are problems that today's teams are facing. When you use Docker, you are not dependent on any machines or operating systems. You depend only on the images that you create. The image contains everything. Image contains the operating system. No, it doesn't contain the operating system, but it contains the necessary libraries and binaries to make it look like an official operating system. You can log into this machine literally and work on this machine just like you would work on your laptop, but operating system is not there. It is actually on the host machine where it is running, and it's completely at the same time it's completely dependent on the host operating system. The same container can run anywhere in any operating system. It should be, if it is a Linux container, it should run on Linux. That is the only thing. Doesn't matter which flavor of Linux, it can run anywhere. It's completely independent of the operating system. So it contains your running program along with the environment, and so you don't need anything else for your application to run, right? It's all contained in the image, and when you run a container from this image, the container will contain everything. And the container run inside a machine something like your laptop or the developer's laptop. You can install Docker in a machine, then you have the option to create the containers. And then later what we can do is, assume you are running some 4 or 5 containers in your laptop. They are very lightweight containers. You want to test some PHP application, so that you use this container for that. You want to test some Java application, you use this container for that. You want to test some Python application, you use a separate container. You want to check some JavaScript applications, you create separate containers for different purpose. And when you are done with testing, you will just delete these containers. Maybe take a image and delete these containers. Later when you want to work on the same application, you take the image, create a container, then work on the code, and when you are done, then commit the new image. So the image always contains your source code, the code that you are developing, along with its runtime environment, and it can be shared with anyone. A different guy, a friend of you, can get this image, then run a container from this image. He get the same environment the other guy had in her laptop. It sounds great, right? And generally what every company does is they will keep one registry, and inside this registry every images would be there. One image for the shopping cart, right? Think about a retail company. One image for the shopping cart. This image contains the shopping cart programs along with the environment, maybe a Java environment or PHP environment, whatever. Maybe this contains the web application. It would contain a web server along with a number of static files to be displayed on the user browser. Then this contains the prime customer. It is nothing but a PHP application, an application written in PHP, and it contains PHP runtime. So like that, every company will maintain a registry for themselves, and whatever application they have, they will keep them as the images. The image can be downloaded by the developer when they want to develop the image. The image can be downloaded to a test environment when you want to run some testing in the testing environment. The image can be downloaded to a development environment, to a staging environment, to a production environment. It doesn't really matter which machines are running the image, they are actually running the same thing, they are running the same container. So the shopping cart need to be tested, or the developer has an interest, he want to work on the shopping cart. He download this image, he create a container on his laptop, he will make the change in the code. When he is done, he will commit the new image. Then this image need to be installed on a development machines. All you do is create a container, and it takes couple of seconds to create a container from this image. It's that fast. You don't need to worry about installing PHP before testing shopping cart, because PHP is already there inside this image. No need to install anything extra on the operating system. Same container, when you want to deploy it to development environment, it's all about creating a container from that image. So this is how it works. In every environment, same image is deployed. If there is a problem, the problem is reported to the developer. Developer will take the image again, then he will make the modifications, then he will update the changes in the image, then he will create a new image. He will fix the problem, now add the new changes to that image. Now the new image can be used by the people. If it is working, then the same image will go here. If a problem is found here, again the problem is reported back to the developer. He will fix the problem in his laptop, make the changes, and modify the code image accordingly. Then it is tested, it is verified here, then again further tested in this environment. Finally you deploy that into production, make this change available to all your customers. So you get a unique or ideal infrastructure across, from the development team's laptop till production. So that's a great thing in Docker. Otherwise, maybe the developer run Windows operating system. In testing environment, you have a different operating system, and by mistake in development, it run a different version of PHP installed in it. These kind of issues will never happen when you use a containerized. Docker is nothing but an example of a container runtime. So yeah, that's the advantages that you get when you use containerization. Okay, fine. And how about your production? Your production contains multiple machines, right? So generally, what I discussed in the earlier cases, maybe one Linux machine which will run the shopping cart application, right? So using the package manager of this operating system, you would install PHP or whatever. Then you will deploy the shopping cart application inside this machine. with necessary environment manually installed in it. And like that, you have a number of machine in production. This was used to be the case which we have been discussing in the previous classes. So now think about this. You are replacing all these machines. All you create in production is just the Docker host machines. Let's say you create some, you have some 10 physical machines. Assume these are physical machines, something like your laptops, part of your production infrastructure. And you have set up Docker in each and every machine. Just like the developer installed Docker in his laptop, the same Docker is installed in each and every machine. What that means is you have this registry, and this registry contains some images which are tested and verified, some images which are yet to be tested, some images which are not at all tested. So there are different images that you validated, and some images that are working fine. The same image you will run as containers inside these Docker host machines. Maybe the shopping cart, you know that there are many customers using the shopping cart, so one container would not be enough. You might need some 10 containers to run the shopping cart. What you mention is, from the same image shopping cart you would create 10 containers. Then 10 containers will run across these machines. Some container will go here, some container will go here. So across your entire infrastructure, it will run the number of containers that you specify, and all created from the same image. So they all look identical as well. Then you have a payment component. This is that image, and you want to run some, let's say, 5 containers, because it is getting load but not as heavy as shopping cart. So you need less number of containers to be running. So you take this image, then run one container here, one container here, and one, like that you would spread 5 containers across different machines. So all this container run independently on these machines. You don't need to worry about them. There is no, you can run shopping cart and payment containers on the same machines, no problem in that, as long as the machine contain enough hardware resources, the CPU, memory in it, those requirement only you know that about your application. So the machine should have these requirement. That is the only criteria. Any number of containers can run completely independently on any number of machines. There is no problem in that. So you can achieve this kind of uh, it's easy, right? You don't need to worry about installing software in these machines, right? You have thousands of machines in production, so you develop it just like a Docker image, and you will run the runtime inside these machines, and they will serve your customers. So these are the advantages when using Docker. Docker is one of the most popular containerization tool. There are other things like Rocket. There are few other things also. Docker is the most popular one. And one more advantage with Docker is its resource utilization. Let's say you have one machine, a physical machine, or you can call it a Docker host machine. And inside the Docker host machines, you are running a number of containers. And these containers, even though they look like an operating system, maybe it is not an operating system. It is just a lightweight container which contains your application and whatever your application need to run. That's what a container is. I already told you that. And in Linux machine, there is something called kernel. Kernel is nothing but he is the one who decide which Linux process need more memory, which Linux process need more CPU, then assign the CPU and memory to those process. And the same Linux kernel which is present on the host operating system where Docker is installed, it will take care of every container's requirement. For example, this container is running some execution. It runs the shopping cart component, and a lot of people are using the shopping cart component. People are creating shopping carts and doing different actions. So in such a situations, you want to make sure that you are getting enough CPU and memory to run this application. So the kernel will detect that and give the necessary CPU and memory to that container. Maybe at that point of time this container is not doing anything, maybe it is running some database applications, but right now there are no transactions coming to database. This container does not need memory, it can free up the memory. So the memory will not be assigned to this container, so it will use efficiently, just like the Linux would use memory and CPU for the process. The container would consume the CPU and memory, and it's all managed by a single kernel. Whichever container need it, it will give it to it. Whichever container does not need it, those memory and CPU are free, can be assigned to a different container that needs it. Right, this is not the case when you create a virtual machine. I don't know whether you heard about virtual machines. It's possible if you have a laptop, you can install some hypervisor, then you can create dedicated virtual machines. You can create, split your laptop into small virtual machines. You have 10 CPU in your laptop, 2 CPU you give to one machine, 2 CPU you give to one machine, then 2 CPU you give to other machines, then the remaining 4 CPU you use it for your laptop. So something like that, you can create multiple machines within your laptop with virtualization. This is not containerization, this is called virtualization. In this particular case, what actually happens is every machine should need its own CPU and memory, and they won't free it up, right? Whether you use it or not, you are running a shopping cart application in this virtual machine, it need to use, or whether it has a lot of requirement coming or not, it can use 2 CPUs, not more than that, not less than that. Whether it is using or not, the resource won't be free. That is not the case with containers. The containers memory and CPU are managed in the same way the Linux would manage the process memory and CPU. So you save a lot of CPU and hardware resources, thus save a good amount of money if you migrated your normal applications into container based applications. It's also equally important that even though it is not mandatory, if you have a big monolithic applications, you have a big application called payment, and the same application contain credit card payment system, debit card payment system. So it's a very big software component. So such components are not recommended in Docker, but they can run as smooth as they would run on a virtual machines. But to get the full advantages of Docker, you would make them very small services. Maybe credit card is one service that you develop as a project. Debit card is another service you develop as a different project. So like that, you split your work into very small, if possible, the microservices. So then you will run these individual services in individual containers. This is how you make the full use of containers. So they are absolutely isolated each other, and also you know about each and every containers, right? If you know how much transactions are coming to the credit card, it's very easy to monitor now, right? You have a container, just monitor the container, how many transactions are coming here, and just monitor this container to monitor how many transactions are coming for the debit card. Then other one takes care of the net banking payments. So it's a good idea that when you use Docker, split your big monolithic application. That is a lot of work for your development team, yes, but it's worth doing it, right? Trust me, it's worth doing it. Split the monolithic application to small services, then run them on a Docker container. It would be great, a big great practice that you should always keep in mind. And you would eventually, I mean, if you are a developer, you should start implementing such things. And also, if you are not a developer, you should give suggestion to the development team about the importance of migrating to the Docker. And if you have to migrate it, also consider splitting your monolithic applications into very small individual services, so that they can run in a smooth way when you are using the containerization services. And it would become more smooth when it comes to the orchestrations, which we will talk about. So I hope it's any questions that you have, feel free to put them in the chat. I will talk about them at the end of the training. Okay, so the next thing we will talk about, the container orchestration. That is the next topic. Right? So, yes, now think about this. Your company has started a culture of writing things into containers, right? Developing applications as small services, right? One is for credit card, one is for debit card. Then the prime customer application is also split into small feature based operations. Maybe the benefits of the prime customer is one service. Then the discounts of prime customer is another service. Like that, you try to split the things into small monolith, small microservices as much as possible. And assume your company already started with that and it's going great, right? Different developers have learned how to develop the application using Docker. They know how to install Docker in their laptops. Now they know how to make change in the source code. Then with the changes in the source code, how we can create new images which contains the changes. So all these things they learned and they practiced, and assume a new culture evolved in your company, across your development team. They are now working using Docker. The testing is done using Docker. The development is done in Docker containers. Then right, the deployment team take the Docker and then run them on the development testing or different environment. So a new culture has evolved. What I'm talking about is hundreds of Docker images, or maybe hundreds of services that you want to run. So you have a production infrastructure which contains, which you're getting a lot of traffic, right, coming from the people. You have lakhs of people browsing your website, applying some items, right, ordering few items, using the shopping carts, using the payments. So there are different things that your customers are doing. So sometimes the traffic can be very high on your infrastructure. You need more CPU and memory for your infrastructure. Sometimes the traffic is back to normal, everything is back to normal, then you don't need too much CPU. You can delete some of them to save some money. Sometimes a service can fail. Maybe a container is running in your production infrastructure, it can fail. Then in such cases, you should automatically create another container that can replace the container that had failed. Or sometimes you want to automatically add more containers when there is a situations, then delete the containers when you don't need them, right? There are many things. You want to also make sure that all containers get the equal load. You are running some 10 containers for shopping cart, all 10 containers should get equal load. So there are many things that you need to take care when we talk about a production infrastructure. So how do you achieve it when you are using containerized development? For that, you need to use some orchestration tool. In this orchestration tool, you will write down what are the different methodology that you need to use. You can mention, for the shopping cart application, I need 5 containers to be running always. If more load is coming, I need to increase the number to 10. If the load is back to normal, again it will go back to 5. So I define something like that. I define a service called shopping cart, telling this orchestration tool. Kubernetes is an example of an orchestration tool. So I tell different thing. I tell that for the shopping cart application, it will always run 5 containers. The image is all images are there in the registry. Your development team have developed it, tested it, and the verified images are kept in a stable registry from where you can download, or this orchestration tool can download them from here. So you are telling this orchestration tool, for shopping cart I need 5 containers to be running always, and all 5 containers it should be there. In case one container got deleted, automatically a new one should be created. So I can mention that also. Then I can also mention that when I have to make some change in the shopping cart, because my development team work on the shopping cart, sometimes they make code change on the shopping cart. At that point of time, this is how such changes should be applied into the working containers. Right now I have 5 containers running, but sometimes I will change it, I will modify the image, I will update a new image in the registry. So in such a situation, the orchestration tool should take that new image, then create new pods using the new image, then eventually delete the existing pods, then the new image would be. So this is what you call deployment, right? You make some change, your development make some change, update the change in this image, the image would be pulled by an orchestrator which know what to do, right? It's a automated tool, not human, right? It's an automated tool, Kubernetes. You tell the orchestration tool, if there is a new image, this is how you should update it. You should uh, take the new image, pull it from here, then replace the old 5 containers with new containers created from the new image. And don't delete all 5 containers together, because my customers are using it, it would be affected. So delete one container, create one extra, delete next one, create one extra. So do that way. I can tell all these things to an orchestrator, he will take care of these things. I am also in a situation to roll back, right? I did one deployment, now my new containers are running the latest code, then I quickly realize that there's a problem, something is not working, or a developer made a mistake, and now that mistake is in production. I want to roll back. I will tell this orchestrator that there's a problem, please roll back. What it will do is it will delete the new pods one by one, create the pods from the old image automatically. It all would happen in a matter of seconds. Think about that, right? So this is what I call orchestration. I define my infrastructure. I define how my containers should run, from which image it should run, how the rollback should be done in case of a problem, how the deployment should be done in case of a change in image. I tell everything to an orchestrator who will do all the things in a completely automated way. I can also tell that more traffic is coming, then create more containers, not 5. Maybe increase the number up to 10 based on the huge load that it is getting. Then the orchestration would obey that. Automatically, whenever it is getting more load, it would add more machines into your infrastructure. So the orchestration is more like how my containers would behave, right? Or how my production infrastructure should behave when it is running a containerized stack. Kubernetes is a tool that you can use for the container orchestration, right? So Docker and Kubernetes is the main, actually the major tools being used in the industry today. This is where you should get started, right? So get started with Docker. So what you need to, how do you get started? There's a website called hub.docker.com where you can find a good amount of Docker images, right? A good amount of Docker images. You can see one Ubuntu image. If you run, let me log out. Go to hub.docker.com website, then click on the explore button. You can see a lot of images. You want to search for something, you can search for something here. There's an image called Ubuntu or they say, yeah, if this is an image that you can download from here, then run a container from this image. So learn in first you take a Linux machine, install Docker inside the Linux machine, then learn how you can pull the image from hub.docker.com. Then from this image, how you can create a container. All these things you learn. Now you learned what is an image, how to download an official image from hub.docker.com. Then you create a container from it. Now you run the container, just you are happy to see some container is running, get started. Now you try to log into this container, learn how to log into this container, right? I mean, this is the approach that you should learn. I mean, just looking at the Docker documentation would actually put you into a blank spot. That should not be the case. This is for to get you started. So first you learn how to pull image from the Docker registry. Second thing, run a container from the image that you pulled. The third thing, you log into this container, just log into this container and do something in this container, maybe install Python, install PHP, or install whatever things that you want to install inside this container. Create a new image from this modified container. So now your new image contains whatever you installed also. So what that means is, anybody create a container from this image, that container will already contain PHP or Python or whatever you installed in the previous steps. Then also learn how to push this image that you created back to hub.docker.com, the Docker registry. You downloaded image Ubuntu from hub.docker.com. What you can do is you can create an account yourself in hub.docker.com. Then you can push your custom images there. It's free. It's free. So learn how to push the new image that you created back to hub.docker.com in your account. Okay, cool. So do these things first to get started. The next thing, learn how to develop a image. Take a sample PHP program, run a container, and next thing you learn how to run a sample PHP program or sample Python program in a container. Then from that container, you take an image. So rather than creating the container and taking image, there is something called Docker file. This is for developing a image from the scratch. You create a file, a text file. Inside this file, you will write some lines. The first line would say, take the image Ubuntu from hub.docker.com. Then copy this PHP program into this particular container. Then install PHP. Then execute the PHP program. So like that, line by line, you write these lines. So just learn how to develop a Docker file. It's pretty straightforward. It's like a text file. There's a one line where you can mention from which image you want to start. Then on this image, you want to install PHP. After that, you want to copy your PHP program in it. Then you want to create a final image. And this final image is what the image that you developed, and maybe you want to make some change in the code, again make some change in the code, run the docker build command again, then the new source code would be added into the image. So this is how you develop the image, rather than creating container manually, then copying the PHP program here, then creating another image. So you create one text file, then write down the steps to develop a image, and the final image that you get would contain the source code or whatever code you had modified. So this is the next thing that you need to do, how to develop a Docker image using Docker file. That's what you should learn. So this is the basic stuff. You are done with the basic stuff, right? Now you start with Kubernetes. Actually, in Docker there are many things, but I'm not telling you that. After, as you learn things, you will understand many things. Then you start learning Kubernetes. Install Kubernetes on a Linux machine. Then you will learn how Kubernetes can pull the image from the registry of the Docker. Then run these images inside. So you do it manually. Again, first you do it manually. Pull the image from Docker registry, run it on a Docker host or a Kubernetes cluster. So in Kubernetes, first you will learn how to install Kubernetes. Then you will learn how to create a Kubernetes cluster. The Kubernetes cluster is nothing but assume a number of machines running Kubernetes, and any of this machine can host. You can consider them to be a Docker host. Any of this host can host a Docker container. The Kubernetes, after pulling the image from the registry, run the containers across the cluster. The cluster can contain multiple Linux machines, right? These are actual machines, the physical machines, or a machine that you got from AWS, or it can be your laptop, right? The normal machines. So you can create a cluster first, learn how to create a cluster. Then you learn how to create a pod. In Kubernetes, it is called pod. You can, for now, you can assume pod is nothing but a Docker container. How to create a pod from the Docker image, all these things you learn. Then you learn how to create a YAML file. There is some option called using some code. Inside a file, you can write down the things such as from which image it would be pulled, which is the name of the pod that should be created, right? All these things you mentioned. When you execute this code, then it would result in the creation of a container, or in Kubernetes, it is called a pod. Then again, go a little advanced. Create a replica set or create a deployment. There is something called replica set, or there is something called deployment, where you would mention which is the image I want to use and how many containers I should create. In case of a problem, how do I update some change? If there is a change a developer is making, how I will update the change. So all these things you write down in another YAML file. Then you apply this YAML file, the image would be pulled, multiple pods would be created, and whatever logics that you mentioned inside this YAML file, all these things would be applied on those containers that you have created. So just get started this way. First, you should finish Docker, then you can start with Kubernetes, and that is how the learning would be. But actually, the thing is that you need knowledge on Linux, some programming, or anything, right? You should have some knowledge before you begin with Docker and Kubernetes. It's mandatory. So those who are yet to finish the previous Ansible learning, maybe what I would suggest is finish Ansible, then come here. That would be more helpful, right? That's pretty much I wanted to discuss.